Today, I want to talk about simulation of physical movement for machine learning with R. Simulation of robot gait optimization using GA. I am Yoon Jung, and we study statistics at Ewha Women University in South Korea. We were interested in physical simulation while studying calculation algorithm. So we started this project, and before beginning talk, I inform you that we are not physics experts. Then let's get started. Suppose there is a ball in coordinate. When you fix the coordinate in R, the ball stays in that position. But on Earth, the balls cannot be fixed in the air because of gravity. The ball falls down and bounces to the ground. This is a simple form of physical simulation. Physical simulations are very useful in industry terms. Possibility can be assessed, and it can reduce trial and error, and it can also prevent accident. So there are many popular software for physical simulation. However, R is free and open source, so it's easy to apply many machine learning algorithms. In ordinary physical simulation environment, any object is possible, but our physical simulation environment is only for our robot. So we made a robot simulation that works by inputting gait parameters as shown below. So I'll explain how we created a physical simulation and optimized gait parameters in this talk. And these 5 are gait parameters. This is table of content. Part 1 is about designing physical simulation. In this part, I will talk about background knowledge, parameter selection and assumption, and also algorithm. Part 2 is about optimizing gait parameters. I will talk about what is GA and how I apply GA to my physical simulation environment. There are 3 background knowledge required for designing the physical simulation. And first is geometry and vector. It's used for present robot in 2 dimensions. And second is dynamic. It's used to solve force acting on the robot. Third is Runge-Kutta method. This method is kind of numerical integral. If we know the force, we can know the acceleration. If we integrate acceleration twice, we can get position of mass. The following position of robot can be identified using third Runge-Kutta method. Third Runge-Kutta method is induced by third Taylor series. As we press for time, so I would like to skip the detail. The following is about parameters and setting of the robot. There are 5 parameters, and parameters determine the trajectory of feet. T is time taken in 1 cycle. This is 1 cycle, and T is time taken in 1 cycle, and then S is gait width, and big H is gait height, and small h is pelvis height. And bias is difference between X value of pelvis and X value of center of foot. And there are 6 settings. They are dimension of robot. And we made 2 assumptions for convenience of physical calculation. The weight of any part except head is negligible. So the center of mass is always head. And second, each foot is made up of 2 points, toes and heel, not soles. Assume robot gait cycle is as follows. Right foot move like this, and left foot move like this. Two graphs show the center position of foot coordinate over time. X value and Y value of left foot and right foot intersect perfectly. We can look at the movement of foot. The soles of feet were constructed parallel to the angle of sight. I mentioned the robot setting and trajectory of gait. And now I'm going to introduce to create a working algorithm for the robot. As the robot moves, it generates rotational force, so the angle of sight is not always zero. We mentioned the trajectory of foot. As the robot moves, the angle of sight changes and the position of feet change accordingly. This is center of foot point vector, and this is rotation matrix, and this zeta is angle of sight. It is toes and heel point vector. It also used rotation matrix. Now we know the coordinate of feet. We can see how many points touch the ground. Below is number of cases the robot can have. In first case, no point touch the ground. And in this case, only 1 point touch the ground. And in this case, 2 points touch the ground, and they are same foot. And in this case, 2 points touch the ground, and they are different feet. And 3 points touch the ground, and in this case, 4 points touch the ground. Now let's solve the fourth of the cases that robot can have. The forces we consider are friction force, gravity force, normal force, and moment. Based on the forces, we solve the forces acting on the robot according to the case. If robot doesn't touch the ground, only gravity acts. The force when 1 point touch the ground is as follows. Force acting on x-axis is friction force, and force acting on y-axis is sum of gravity force and normal force. And force acting on angle is moment, which is rotational force. It's a bit difficult to calculate, but we can solve it by recalling the law of right hand. Force acting on x-axis and y-axis are the same if 1 point touched or 2 points touch the ground, but it's difficult to calculate each normal force when 2 points of same foot touch the ground, because 2 points don't have exact same normal force. Therefore, we use zero moment points. If zero moment point satisfied, the robot's moment is zero. But if it's not satisfied, assume that a center of foot point is only touched. This point only touched in this case. If this formula is satisfied, moment is zero. Next, let me tell you a few more assumptions about the simulation for convenience. If 2 feet touch the ground by 1 point, it's assumed that one of the 2 points has high x value only touch the ground. If 3 points touch the ground, it's assumed that 2 points of foot touch the ground. If 4 points touch the ground, it's assumed that 2 points have high x value touch the ground. Next is position and velocity constraint. When foot digs in the ground, like this, reposition the center of mass and lift the robot to the ground. In other words, this process is about vector calculation. Also modify the velocity by differentiating reposition center of mass. And next is numerical integration to obtain following position of mass. Previously, we found the force of the robot using Newton's law and find the position of mass and angle of sight by integrating the acceleration. Final step is getting position of robot. Just before we get a new position of mass and angle of sight, we can draw robot's body by using it. We can get coordinate of pelvis and knee points by using trigonometric formula, and then multiply the rotation matrix, like previously obtaining the vector of feet. There is something to be checked before returning to the first stage of the algorithm. In some cases, robot loses its balance while working and falls. If the angle of sight is over 45 degrees, the robot leans heavily, so we assume that the robot has fallen and stopped the simulation. Then store and image robot's position while returning to the first stage of algorithm. And if robot doesn't fall, repeat this 500 times. Imagine on the plot, the picture shows the robot position when first iteration. As such, the algorithm is repeated to draw 500 images. And in this case, robot falls at 41st iteration. Merge 500 images at 0.01 second interval using animation package. If the robot falls, it keeps stopped in the applicable state. This is further on time. And in the case below, the maximum x value of center of mass is 0.297. As such, physical simulation algorithm is constructed. Now, using genetic algorithm, one of the machine learning technique, we want to find the fastest walking robot for 5 seconds. Then what is genetic algorithm? It's simple. First of all, giving range of each parameters, then take 20 population samples from range randomly. They are first population. Then select population with high Y value. Then mix the selected population appropriately, then pick 20 population samples. Then force a change of part. Then we get a second generation. The more generation go on and on, the greater the Y value. Our goal is using GA, find parameter which make global maximum of X value of center of mass. Therefore, we apply the physical simulation algorithm we made to GA. Fitness value is maximum center of mass X value of robot in the generation. This green line is first place winner by each generation, and the fitness value increases as the generation passes. This is generation. And in this case, first place winner of first generation's fitness value is around 1. And I will show you the first place winner of first generation. This is first place generation, and it falls in the middle. Maximum X value of center of mass is 1.038. It's around here. It goes to this point and far back. Next is fifth generation. It works well, and it easily exceeds to the point where first generation went. Maximum X value of center of mass is 1.822. And this is 20th generation. It works more farther than the previous generation. And in 100th generation, it works farthest. Maximum X value of center of mass is 2.619. It's maybe around here. Then rat race, first place winner by generation. New generation works farther. And we thought gait cycle period and gait width are important variables, so we fix other variables and draw three-dimensional graph with only those variables. The red point is the value of variable optimized by GA. It looks like GA found global maximum. Finally, it's the conclusion of this talk. Though it was only for our robot, but we created a physical simulation space, and we conducted machine learning in physical simulation environment. And working varies according to the parameters, and we found parameters that make the fastest and best walk. And we were able to watch the evolution process using R. And if you want to know my R code, please come to my GitHub. This is my address. And thank you for your attention.
Thank you. Do you have any questions?
Just about curiosity. The first generation of your robots falls, and I understand, well, he falls, so he stops. But for the 5th and 20th and 100th generation, the robot just stops. It doesn't fall. So, is there any reason why you say that the robot stops? I mean, besides falling, what is the reason for the robot to stop besides falling?
You are asking about that? It's not.
I think in some cases you don't see the robot fall, but it stops anyway. So I think the question is, why is the robot stopping if it doesn't fall? Is that I'm understanding that correctly?
This is only 500 iteration. I make 500 iteration.
But so the robot stops only if it falls, or it can stop for other reasons.
She will be respond.
I will answer the question. For the first generation, they just fall down, and for the 20th, 5th, they just go to the local maximum, not the global maximum. In 100 iteration, they go to the global maximum. That's why they just stop there. Yeah.
Thank you. Yeah.
Have you made any studies about deep reinforcement learning? Because we hear about DeepMind experiments with humanoid that can walk by itself just without any physics around, just by reward.
I'm so sorry, but I'm not native, so can you speak more slowly?
Yes, I'll try to rephrase. Correct me if I'm wrong. Have you tried any learning of the robots without any physics model behind it? Apparently, DeepMind or Google gets these robots walking without any physics. They learn on their own the rules. Have you tried any of that? Are you aware of anything like that?
I'm not physics expert.
In the
I am not physics expert, and I'm studying statistics, and I just trying this simulation for learning algorithm. So not yet, but I want to do that.
Great. Does that address your question? Great.
Hi. One question about the gait, the parameters of the gait you're optimizing. The feet are always the horizontal velocity of the feet is a sinusoidal movement, right? So the feet touches the ground, and then the relative velocity is 0, and then it accelerates, and then it slows down at the end, and then it lifts up again. So if
Maybe you're talking about here?
well,
I differentiate.
no, or if you just look at the robot walking, it's kind of walking fast and then slow again, and then moving faster and then kind of stopping again, and then moving again, and then kind of slowing down again. Because the feet are moving in a circular motion like this, and then like this, but when they touch the ground, they basically have no horizontal velocity. And I was wondering if you chose it deliberately to get a challenge for the GA to optimize over. So, I mean, that's why it falls over, right? Or if you would consider adding more parameters to the gait so that you could actually make that more smoothly.
Okay, thank you. I will check that. Thank you. And what's the question again?
I'm gonna summarize, trying to convey the spirit of what you just said. I'm not an expert in this field at all. So it sounds like he's suggesting you could add some more parameters to your model to model the difference in the speed of the robot that it's apparent from this circular movement and then like the zero speed on the when the feet are in the ground. Have you tried more parameters in your model to model this change in velocity that may have been happening?
No, but it's only 5 parameter, and it was I searched in Google, and many people use the 5 parameter in humanoid paper. So I did that, and there are many gait type, and I want to do another thing forward, but now I just do only this type.
So the gait is actually like a standard kind of model in this field to analyze. With these parameters are standard.
Yes.
Okay, thanks.
In paper, a lot of papers.